Okay, I'm going to get to talk about my specialty, which is geothermal energy. I am a terrestrial geophysicist in my day job, specializing in developing geothermal energy. But I think there's some possibilities of using this in deep space or at destinations interstellarly, and that's what I'm going to talk about today. My co-authors, Sai Liu and Shubhajit Bhattacharya, are also here at the University of Texas. They have started in on the modeling, which I'll get to in a bit. So, problem. For going interstellar or going out deep in the solar system, we're going to need infrastructure. We're going to need facilities. But particularly as you go out, there's problems with the existing or likely sources that we're going to have. In particular, the solar flux drops off, so you can go to huge solar panels or look for other things. Deep space probes so far have dominantly used radiothermal generators, basically just a big pile of radioactive material that's hot from the decays. You string essentially a thermocouple across from the hot side to the cold ambient, and you generate electricity off of it. Very good and reliable, but it does have its drawbacks. One, it's a radioactive source, so that's why you see the power plants, unlike Voyager and such, out on a boom away from the rest of the probe. The output does decay over time. It has a definite half-life. And those type of power plants do have a bit of a mass penalty. Solar panels, yet they're great, but they've got their own issues. I already mentioned one, which is the inverse square law of the irradiance. And they wear out. They also degrade over time, as we see here on Earth, for some reasons that are same, some would be different in space. But they would need periodic replacement or refurbishment. And I am focused, by the way, on planetary body power sources. So, not just free-floating spacecraft, but installations on fixed planetary bodies or moons. And if you're on a moon with solar panels or any body, assuming there's rotation, you may or may not have 24/7 power source. That's a problem we have on the moon, for instance. Fission reactors, yep, that's a fairly mature technology. And, we're hopefully getting closer to standardized, if you could call them mass-produced, small or micro-modular reactors that might have some crossover into space. But there again, you have problems of radioactivity. They have infrastructure. They have a logistics tail where they need refueling eventually. They're relatively complex with relatively high O&M costs. And again, you've got a mass factor, mass penalty. Fusion reactors, potentially great, but we're not there now. And they would probably have a lot of similar problems to fission reactors as far as being something you would haul out deep into the solar system. So, the potential solution, which I'd like to throw out there, is geothermal power. There is potentially a lot of it out there. Here's an illustration which many of you are probably familiar with, geysers on Enceladus. There are geysers or plumes, depending on how you look at them, on a variety of moons in the outer solar system as clear evidence of subsurface oceans. So hold that thought. I'm going to back up and do a little geothermal 101. And by geothermal, I'm not talking ground source heat pumps for your house. I'm talking on Earth, drilling typically kilometers into the ground, getting to temperatures way above boiling, and using that heat to generate electricity for use on the surface. This is, some aspects of it are pretty mature technology. We've been generating electricity from geothermal power for over 100 years. But there are new techniques coming online right now, which is my active day job area of research, that offer some interesting promise for use in space. Generally, at least terrestrially, 130 degrees C difference between your deep heat source and surface ambient is a good rough minimum that you need to make economically viable geothermal energy. Some of the advantage of geothermal is a well-managed system can have an indefinite lifetime. I mentioned that we've been generating electricity for 100 years. That plant in Italy, Larderello, Italy, has been running for over 100 years. The oldest plant in the US, the geysers in California, has been running since 1960. So you can manage them as a essentially renewable resource. They have, or the newer ones tend to have very low O&M costs. Geothermal doesn't have a logistics tail. You don't have to refuel it. So that's a significant advantage. And the newer approaches are relatively, I should have put quotes on that, relatively simple. The one significant downside I'd say is you're not working with as high a temperature difference as a fission reactor or some other power sources, so your efficiency will be a little bit lower. A geothermal system on Earth looks, there's varieties around this, but generally, again, you're drilling 0.5 kilometer to 5 kilometers deep, some of the newer systems, including here in Texas, to get to that temperature differential you want. You could be accessing heat from a magma body. You could just be accessing the heat flow from the Earth through thin crust or other sources. But the key is that you're tapping that difference in temperature. On Earth, they've been, up to the present day, mostly semi-open or semi-closed loops, but the newer systems that are being developed now are true closed loops, which I think would be also a key aspect of employing them in space. So, in this, will focus on icy bodies, but I've also done a little bit of work on doing a very distant cousin of this on the moon for power in the polar regions, and I'm happy to talk about that in Q&A if you want. But the key to this is icy bodies. Why? Because many icy bodies in the outer solar system have subsurface oceans. That's a key aspect. So you've got a subsurface ocean, which, and this is kind of back of the envelope level analysis right now. So I'm going to assume roughly 0 degree C ocean, just at freezing temperature. There's a lot of things that can affect that, yes, I know, and we're starting to look at modeling those effects. But the key is essentially a constant temperature subsurface ocean at 0 and a very low surface ambient temperature, typically minus 150 C or so, give or take. I'll show a spread of data on that in a minute. So right off the bat, what you've got is a potentially exploitable temperature difference of 150 C or so. So hold that thought also now. And you see here a typical range of what you might encounter out there. Again, moons with suspected or confirmed subsurface oceans and typical surface temperatures. And you see they vary widely, but use a rough minus 150 is a fairly conservative starting point. You do have another variable which really plays into this, though, of course, and that's crustal ice thickness, which is very poorly constrained at this point. It'll be very interesting to see what the Europa Clipper can determine there. And by the way, we have a pair of university researchers that will be talking about their PI, Don Blankenship, on the Europa Clipper radar, which will be looking into the ice later on in the conference. So keep that in mind. So a range of possible ambient conditions which can provide you the temperature difference you're looking for. Here's a typical configuration of a subsurface ocean. So you have a surface crust of ice of variable thickness, subsurface ocean, maybe heat sources down here, but that's not necessarily a first order factor for what we're looking at. But you do have that ice thickness, and it varies a lot. It can be hundreds of kilometers thick, but also note, in some places, at least theoretically, it goes to 0. Why? Because you've got geysers. You can, depending on, because ice has multiple phases under different pressures, you could end up having a layered system of multiple sets of ices and waters in here. That would probably be detrimental to making this kind of a project work. I'm looking for simple common ice crust with a subsurface ocean, probably a little bit saline there. Oh, if you do that, okay, there, yeah, where'd it go? Okay. So, the heat flux from the bottom, yeah, whatever the source, you got something that keeps your ocean liquid. So a simple configuration, what am I thinking about here? Well, you drill through the ice, in the simplest way here, a coaxial system, something that we do on Earth all the time, so that you have flow up and down using one well. Now extend that well into the subsurface ocean a little ways, put a heat exchanger down there, but you can put heat exchangers in different spots depending on how you work this. And again, exploit that temperature difference. Bring it up to the surface, drive a generator, or drive a solid-state thermoelectric generator, perhaps. That might, that reduction in simplicity might be worth a trade-off on efficiency. But you're just connecting those two temperature differences. Let's see. There are many variations on how you do this, both here on Earth and potentially up in space. You can do multiple well systems. You can vary where you do the heat exchanger. There's a lot to be worked out, obviously, in this. This is still conceptual. You probably aren't going to mechanically drill. We're not going to take a Bruce Willis up in a spacecraft with a drilling crew of roughnecks to drill here. But things that have been explored and tested here on Earth are things like melt drills. Just a heated chunk of something that can, using gravity, melt its way through. Those have been tested in Antarctica. I was really hoping I'd see something like that on the Europa Clipper, but we're not going to. Plasma or millimeter wave, various types of directed energy drilling might also be relatively low mass and easy to transport. Right now in Marble Falls outside of here, is a spinoff out of MIT called Quaise Systems that's experimenting with using millimeter wave drilling through granite right now. They've invented flexible waveguides and tubes to do that. So there's ways you might be able to achieve this without really bulky high mass machinery. The efficiency, because you're actually working a lot closer to absolute zero than here on Earth, you actually get reasonably good efficiency, but again, not as good as if you have a hot side of your equations. If you rough out the numbers, and this is an extremely ideal case, a simple one well system connecting those two temperature sources, ignoring losses due to the length of travel, you can generate on the scale of single-digit megawatts off of a well. That's comparable to what you get off a good geothermal well here on Earth, too. So there is a reasonable amount of power off a single well system. And to scale it up, drill more wells. We have just started to model this, partially because we're doing this out of Hyde. We'd love to find a funding source to explore this more deeply. DARPA. But haven't found that yet, or maybe NIAC, we'll see. But we're really looking for that, because right now all this work has been coming out of Hyde in our spare time. But we started some initial modeling on this, and this kind of provides your worst case boundary. So I showed you the best case of a few megawatts. Worst case is you use uninsulated drill pipe through a thick section of crust. You have a limited ocean. We need to expand that out to essentially an infinite source ocean down below. And here's the numbers that we're using on that. But again, using fairly simple, I think this model did use, I'm trying to remember if we used saline water on this or not, but I don't see that. Minus 175 C case. And you get on the order of hundreds of kilowatts output, typically, for a more pessimistic solution. As with any geothermal system, well, especially when you've got a finite source like the first model had, you get quite a drop off in time, but you settle out and approach an asymptotic steady state on your output. Again, if you've got essentially an infinite ocean, this would change quite a bit. There are obviously some issues with doing this. As a physicist, I tend to like to say, hey, it's just engineering problems, you know, don't worry about it. But they are real, obviously. Drilling to the oceans, yes. A few kilometers, I think that's fairly doable. Tens of kilometers, hundreds of kilometers, okay, now you're talking a lot of issues, including things like what that company in Marble Falls is going to have to deal with. If you're melting your way through a system, what do you do with that waste product? How do you evacuate it from your well? Can you just plate it on the sides? Those kinds of things. The wellbore itself, how stable is ice? It actually works as a rock at that point, but how stable it is are the moons tectonically stable to where you're not going to shear off your wellbore at some point? Those kinds of issues. What's the material you can case your wellbore with, or do you need to? Can you print on spot a good insulated casing for your wellbore, or is there some other solution? Some of these interesting materials could be very applicable to this, and if you can insulate your wellbore, that can really pay off as far as your output goes. For that, also, by the way, I didn't mention it, but there's also another great moon, but we haven't looked at. Probably not very practical to install anything permanently on, but you got Io, which has a molten silicate interior. An earthbound geothermal guy would love to tap an energy source like that, but that very young crust doesn't look very promising for a permanent facility. Huge ranges of things that need to be studied, some of which get a fair amount of attention already, but materials at these very low temperatures. We've obviously been working with metals and other materials that go into spacecraft at these temperatures. I'm not expert in that area, but that's been studied for a long time. What isn't necessarily as well explored is the fluids. So you're taking an earthbound geothermal system and essentially shifting it 200 degrees to the cold side. Water, it probably isn't going to be your exchange fluid, your heat transport fluid in this case. What are some other fluids you can use that have the right properties at these temperatures? I think we're running a model now with helium in there, so that would be interesting to look at. Yeah, the power plant design. Is this going to be an open or closed system? The newest systems that we're starting to employ here are completely closed systems, so you're circulating your same fluid through all the time. Do you need to worry about that on the moons? Can you just have an open system and just pump one way? That might be easier to do. How could you construct this? Yes, robotics, 3D printing. What would you want to assemble in advance? What would you want to build on spot? And what could you build on spot with the materials at hand? If you're on an icy moon, all you've got is frozen water and maybe some other trace things. What about the thermocouple side? On Earth, we're always using turbines. You flash something to steam, you make it drive the turbine, drives the generator. Yeah, that can be done. You're talking potentially a mass penalty and complexity. We do 3D print jet engine turbine blades nowadays. That can be done potentially. But I really like and would like to find someone to cooperate with this are the thermoelectric generators, the solid state, no moving part thermocouples to generate electricity off of a temperature difference. I think they're improving in efficiency, and I think that offers a lot of advantage in these kind of situations. Superconductivity could also play a factor here, a supporting factor here. So I always watch, you know, what are the temperatures we can get to with that now? So where can we apply this? Well, you know, we have a moderate grasp of what bodies in the solar system have this kind of configuration with the subsurface ocean. What if you go further out? And now we start to look at the interstellar. So this is a little bit of an old plot, but you still get the idea here. There's a zone of exoplanets found with the right conditions that might be icy and therefore might have subsurface oceans also. So potentially destination spots, but also others. So this is all about location as far as where you can do this, because you do need a fairly large solid body. But we don't know yet essentially how far out those go in the solar system. But as far as we've been, there's reasonable evidence of that, including perhaps Pluto. So, will we find stuff like this all the way out to the Oort cloud? I don't know. I mean, obviously it's very cold, you can cool down, but we found surprising situations where internal heat is generated one way or another enough to keep subsurface oceans viable, even on a very, very cold body. What are the use cases? Well, it looks like on the order of megawatts could be generated. Now, that's not going to power an interstellar ship to a high fraction of C, but you've got communication nodes. You've got things like missions to the gravitational lens point. You've got those kind of ideas. And that was one of the things that got me going. Also, Claudio Marcone's work in that regard. But potentially, maybe you could scale up. If you're willing to tap hundreds of wells, you might, or thousands of wells, you might get up into the gigawatt range as far as power goes. So maybe you could use it that way. But whatever the needs are, there's a potential for a powered network or infrastructure network in the outer solar system, maybe way beyond, because these icy bodies are looking fairly common in the universe. Now, you do have a geometry problem because you're tied to bodies that orbit. So, you're not going to get a uniform distribution of power plants in your solar system. This happens to be, I just took this off of here at the Planets Today to find where are the main bodies right now. And so if you wanted it for network architects in the audience, you can kind of look at that and go, okay, yeah, it's great if we're going in one direction, maybe not the other. You're doing good. So that's the idea in a nutshell. I'm happy to take questions, collaborate, take pot shots at me. This is a back of the envelope level calculation now. We're just getting into modeling, but I will point out where the current probes are heading to, Europa does have evidence of plumes, which tells me at some point the crustal thickness goes to 0. Yes?
All these worlds are yours except Europa. Attempt no landings there. Somebody has to ask, planetary protection. How much scientific data do you need down a borehole before you can declare it's sterile down there, I can conduct industrial operations?
That's a fair question. That's not within the scope of what I'm looking at here. So, maybe we'll know enough from the plumes, flying through the plumes to figure that out. But no, that's not my call. That's an ethical call and a different type, maybe even a legal call on whether you would, if there are microbes down there, if there's life down there, yeah. And, are you going to do that? I wouldn't advocate it at that point. Yes?
What is the state of the art of knowing what the composition of that fluid coming out of the plumes is?
I would rate it as very tenuous. There hasn't been what I would call direct measurement of the content of that, but the methods that have been used by the probes that have gone by seem to indicate something roughly like our ocean level of saltiness. There's probably people in the audience that know that better than I do. Or we've got the PI, Don Blankenship, on the Europa Clipper talking later. He'd be a good person to ask on that. That will have an impact on the freezing temperature of the ocean, which affects your base temperature, your heat sink, but also pressure affects it a lot. So you can have quite a range in actual temperature you would expect that ocean to max out at, or to freeze at. Yes?
What are the important considerations for the working fluid? You said that water is probably not going to be good. Helium might be something that we could consider. But, between those two extremes, what are the physical principles that really matter?
It's a matter of it, one, staying liquid, liquid or gaseous through the range. On an Earth-based system, you control the pressure. You keep, typically, if it's hot water, but also carbon dioxide can be used, refrigerants are used, but you keep them under pressure until you're ready for them to flash coming into the turbine and drive that. So you need something that's stable over that temperature range you're using in a gaseous/liquid form with the pressures you anticipate using too. You can affect that a lot by doing a fairly high pressure system, but that costs energy. You can do low pressure. You can take advantage of the vacuum on the outside if, again, you're doing a one-way system instead of a recycling system, and use that pressure, absolute pressure drop to affect this. But let's see, is there anything else I'd add on that? Yeah, to my knowledge, that's a totally unexplored region as far as, because there isn't any funding right now to look at these areas to start to explore. I mean, you can look up something like the CRC book and see, okay, I see these things are gaseous or liquid at these temperatures, what might work? But I think there's a lot more to be done there.
So like with the turbine system, then the assumption is that there's some kind of phase change that goes along with it.
Right.
But in a thermoelectric system, it can all be single phase?
Yes, yeah, theoretically. And I really like that type of system as being much simpler and much more readily employable in these remote conditions. And there's a variation on that I worked with General Electric to propose for the polar regions of the moon, where you just essentially string a thermoelectric generator across the lip of a polar moon crater and take advantage of constant or near constant sunlight on one side, permanent shadow on the other, and just generate electricity off that. The moon regolith happens to be an incredibly good insulator. So that's why you can do something like that and get a very high temperature difference across a very short lateral distance. General Electric threw in the idea of orbiting mirrors to make the hot side hotter. But we did propose that to DARPA a couple of years ago and made it through the first round, but got cut in the second. Anything else? Oh, yes.
Yes, so going back to the planetary protection considerations, it's hard to conclude, even after extensive study, that there is not life, on some of these icy bodies. So are there engineering solutions you can think of to minimize your impact?
Okay. That's a good way of phrasing the question, and I appreciate that. You could do essentially a sealed unit if you had a way of transporting it into the subsurface ocean. You'd have to drill a large wellbore, and then, for heat exchange of the temperature, you need a lot of surface area typically. So you might have, but if you've got hundreds of kilometers of ocean, if you can somehow 3D print a sealed heat exchanger that can stick into the ocean for 100 kilometers, then yes, that would be a way to isolate your system, at least theoretically. But of course, you have to deal with issues like, will the system ever degrade? There'd be a lot of complications on that. The flip side of that is you can never completely prove a negative. So how would you ever prove that there's no life under any of these oceans? Not my field of expertise. Anything else? Oh, another one. Yeah.
If you're doing melt drilling, the hot thing is simply dropping under the influence of gravity.
Yep.
There ain't a lot of gravity.
No.
Do you need to put like some gripper pads or something and push it down, or do you just wait?
Well, there's a variety of modes there. You could motorize it if you wanted to. You could make it kind of like a corkscrew and power it. NASA has funded the development of prototype melt drills. And Duncan Young, who is one of the two presenters tomorrow, has worked that subject area and tested probes, if I remember right, in Antarctica. Because they're trying to they use melt probes now to get to the oceans underneath ice sheets in Antarctica. So it is done, but yes, much lower gravity, particularly Enceladus, a tiny little thing. Maybe you would want to do it. Maybe you'd put some pressure onto the wellbore behind it. There's a variety of ways you could do something like that. Good questions. Is that it? All right. Thank you very much.